Hello, I'm Frank, and this is my heat transfer project. So a little bit of background. Refrigerators, to keep food safe, are supposed to be kept at around 4 degrees Celsius, and Georgia Tech campus housing is notorious for having pretty bad appliances. So today we're going to be checking out if, in fact, the refrigerator is at 4 degrees Celsius.
In designing an experiment to measure the temperature of the refrigerator, we can use a transient heat conduction problem where the system is not in steady state and has a time dependence. One method of solving a transient heat conduction problem is the lumped capacitance method, which assumes negligible temperature gradients within the object measured. In other words, this lumped capacitance method is only valid when the BO number is less than 0.1. In our experiment, we're going to use a melting ice cube to measure the temperature of the refrigerator because the thermal properties of water are well known. So to find the temperature of the refrigerator, T infinity, I designed an ice cube where the lumped capacitance method is valid, or the BO number is less than 0.1. So this ice cube has side length L and 5 faces exposed to the air in the refrigerator, while the bottom surface is in contact with an adiabatic surface. Using these lengths, we calculate a volume of L cubed in a surface area of 5L squared, which gives a characteristic length of L over 5. Literature values of the convection constant of free convection in air is 2.5 to 25 watts per meter squared Kelvin, while the conduction constant is 2.22 watts per meter Kelvin. Using these numbers, we use the equation for the BO number, H times the characteristic length over K, and our condition, which is the BO number less than 0.1, to find that our L has to be less than 4.44 centimeters. Applying our lumped capacitance method, we start with the energy balance equation, where E in minus E out plus energy generated equals the change in energy stored. So our assumptions are negligible radiation, an adiabatic base, the temperature of the cube does not change when melting, our dt equals 0, and that the change in volume as a function of change in time multiplied by the density gives us the change in mass and change in time. So using our assumptions, we find that E in our energy balance is 0, while the change in energy stored is also 0 because dt is 0. So we're only left with our convective heat transfer terms and the energy generated terms Q dot V. So moving our variables around, we see that Q dot V equals our convective heat transfer, and then we can quantify our Q dot, our energy generated, by the enthalpy of melting. So the enthalpy of melting of water is 334 kilojoules per kilogram, or 334 joules per gram. So knowing this, we can find that our energy generated during the melting process is delta H times the change in mass divided by the change in time, which is also the change in volume times the density divided by the change in time. So on our other side of the equation, we have the H times the surface area times the temperature of the ice cube, which is 0 degrees Celsius, minus T infinity, which is the temperature of the refrigerator.
So here we have a roughly cubical ice cube, and it measures around 4.4 centimeters side lengths.
The first dimensions were measured at 10:05 p.m. and subsequent measurements were taken an hour, 90 minutes, and 120 minutes after. The measurements were then entered into Excel, and the volume and surface area at each time were calculated. The average surface area was 91.12 centimeters squared, while the slope of the volume versus time plot is negative 0.1124 centimeters cubed per minute. Plugging our values into the equation we derived earlier, we find that the temperature of the refrigerator is around 2.517 degrees Celsius. Our calculated temperature may not be 4 degrees Celsius because this temperature was calculated using an H value of 25 watts per meter squared Kelvin, and in free convection of air, the H value can range from 2.5 to 25 watts per meter squared Kelvin. So if we use a lower H value, then the denominator of our equation would decrease, which would increase our final calculated temperature. So in conclusion,
Eric Bachman, is your refrigerator running?